All right, great. Happy New Year, everybody. Welcome to the first DSG seminar of the year. Today is my pleasure to welcome Dave Doermann, who has a really fancy title at the University of Buffalo. Dave Doermann is the professor in empire innovation and the director of the Artificial Intelligence and Data Science Institute at the University of Buffalo. Dave and I go way back. We were colleagues at Maryland for over 10 years. After I moved up here to Waterloo, he had a stint at DARPA and recently, well, a few years ago, moved up to our neck of the woods. So today he's going to tell us about the evolving face of misinformation in text, image, video, and lots of other content. So take it away, Dave.
Great, thank you very much. So I assume you can see my screen okay. Hopefully the videos and stuff will work that I have. So thank you very much for inviting me. Yeah, it's been a long time that we've known each other, and since I got probably closer than almost anybody else from our cruise at Maryland, I do miss the interaction with everybody, but got a great position here, get to interact with students more than I did as a research scientist at the University of Maryland, and enjoying my time here. So I'll start with the main caveat. That's a lot of this work that I'll show you has been done by myself, my students, and other colleagues that have been cooperating with us on various projects. But in general, my background is in computer vision, document image processing. And when I was at Maryland, there were a lot of work for various three-letter agencies. And as Jimmy suggested, I did go to DARPA for a stint. What they do is they give you a badge with your termination date on it when you start. And that's how they have innovation. I'll talk a little bit about DARPA, but basically you get to stay there for 4 years, and you're in charge, and you're the center of the universe for 4 years, and then they forget about you. So I want to talk today about misinformation in text, image, and video content. The real focus here is what's being done, not necessarily to understand the role that things are playing in our society. That's definitely a big piece, but I'm going to come at this from the computer vision point of view. And I understand that there are a lot of different levels of expertise. So I'm going to keep things fairly general, but I want to give you an idea of what the challenges are that are being faced here in the US, across the world, but depending on what type of society we have, a lot of the different components of what we need to do in order to address misinformation. So the truth is that these types of disinformation and deception, misuse of media occur every day. Here's an example of a United Nations speech in 2017, where this woman basically held up this picture and said, "You need to help us. In Kashmir, there's this violence. These people are being injured." Well, it turned out that that was really an injured woman, but it turned out to be in Gaza City in 2014. And without knowing the semantic information about this, people tend to believe it. It's the same way when you get Facebook posts and people just repost things. I saw one that somebody shared about how Facebook doesn't allow you to post the Lord's Prayer just yesterday. And I looked and did the search. It's been going on for years. Here's another example of a photo of a meeting between Americans and Afghans. Here's the picture that the Americans posted on the left, and here's a picture that the Afghans posted on the right. And you can see a very basic difference. this clock here that was here in the American photo isn't in the Afghan photo. Well, you can ask yourself, why the deception? Well, you can imagine at that time in 2017, the Afghans were really worried about perception. And this turned out to be held not at a hotel, but at an army base. And that's the kind of clock you have at an army base. So it was removed from this picture. And it did pretty well. I mean, you wouldn't notice it, but it's one of those small things that, that we often see. Here's another example. This was an example of a hostage, Robert Levinson, and after a long time after he was presumed to be dead, these pictures started showing up for his family, and they're asking questions now, or did it back then. What's going on here? We were told that the negotiations have really stopped. There haven't been anything for years. Well, if you take a look at this, here's some photos, and they're really bad because I blew it up a lot. But here's a known photo of Robert Levinson. Here's a released photo in 2009 when he was being held hostage. And then there was an FBI age progression in 2011. Well, if you do some analysis of this image, you can see that these photos that were taken here were simply manipulated versions of the FBI age progression photo. So they don't look exactly the same. There's color differences and things like that, but you can see that the hair is exactly the same, and this wouldn't occur normally. So the government in the US has been concerned about this thing for a long time. And as Jimmy said, I went to DARPA in 2014 to address this problem. What you do as a program manager is you get to propose or take and develop a program. And what DARPA does, if those of you are not familiar with DARPA, DARPA was set up to essentially prevent strategic surprise. What happened was in 1959, when Sputnik went over, the government realized, uh-oh, we got a problem. We didn't expect this. What DARPA does is DARPA addresses problems that industry won't address in the coming years, that may be unique to the government, to our warfighters. And in 2014, this idea of manipulating media and providing it to influence in one way or another was not something that was in the public eye. That's different today, but in 2014 then, we started this program called Metaphor, Media Forensics. And the idea was to evaluate the integrity and produce an integrity score for every piece of media that would come through a system. So in this case, the three parts to the program were a digital integrity, meaning can you detect in the image itself, in the representation of the image, can you detect things that were physically changed? The physical integrity are things that would happen in a normal image that maybe you don't see. For example, in this image, there's a wake here in the original part, and there's no wake here. And then a semantic integrity. I'll show you some examples of this, but basically reasoning across all of these things to be able to tell what's manipulated and what isn't. So what's the idea of media forensics? Well, the idea of media forensics here is that we have an image, and has it been manipulated since it was first captured? So here's an example of a stock photo that North Korea released. And these are the kinds of pictures that our government takes a look at. And we want to ask, has it been manipulated? Has it been repurposed? Is there digital evidence supporting whatever hypothesis we come to? So in this case, there was an image here that was released, and they were purporting that this was a landing exercise that occurred in North Korea, and basically to show the strength of what we see here. So we want to also find out exactly what was manipulated or how it was manipulated. and what content was used. Can we provide the provenance of these types of images? So you can see here in the original image, this piece was a copy of this area. You can see almost down to the pixel level that it's very similar. In this case, the landing craft, there's 1, 2, 3, 4, 5, 6 landing craft that are shown on this beach, but in the original image, there are a lot more in this image. So this suggests that there's manipulation here. The problem is we have various people that do this on a regular basis, but they do it manually, or they did at the time. So the question that we want to ask is, can we have a quantitative measure of integrity? And we want to know if that type of manipulation was benign or whether it's something that's important that we need to look at. And more importantly, we want to do it automated, in an automatic way. So really the problem comes down to our inability to assess this media at scale. The problem is right now, and back in 2014, we had huge numbers of media assets. We have people that were dealing with the cameras in social media. We have the ability to take all of this stuff and do expert manipulation, of course, manually at the time. And depending on what type of application we have, we can want different types of information. So if you're going to prosecute something, and this is a big example, for example, in child pornography, you have to ensure 100% that something hasn't been manipulated. Well, if you're doing an analysis or an investigation, you can be you don't have to worry about it necessarily being manipulated, but you still want to know what type of information is there and what the truth is when you're looking at this. And at the time, we had this huge growth of social media, and we really had nothing to be able to detect these types of manipulation. So if you can imagine, an agency that's looking at now millions of images a day and just looking for sort of this proverbial needle in the haystack, you really don't have any way to do anything constructive. If you have even, a good analyst that can produce maybe 1 or 2 reports a day. So what are the requirements? Well, first of all, you need to be able to scale to millions of assets. And we can do that now, but we have huge numbers of false alarms at the same time. We need complete automation. We need to be able to define it quantitatively versus some type of authentication. Authentication says, yes, this is authentic, it hasn't been manipulated, but what does it mean to have something that was manipulated that really maybe doesn't mean anything? So there's no quantitative part. It's hard to go to court, if you don't have these kinds of quantitative things. We have to look for content-based clues, not just manipulation of the media asset itself in terms of the representation or the pixels. And we have to have and look at proof by association. Is this something that's maybe unmanipulated, but is being misrepresented? If we can do partial image search, where we can find the pieces that went into this, because a lot of times people don't create their own material. They just take and cut and paste and use Photoshop to be able to do this type of thing. So here's an example over here where they talk about a massacre in Syria. Well, it was a massacre and it was a lot of dead people, but the truth is that it was 10 years before what they were referring to in this article. So it was a misassociation, and we're really concerned about those types of things. But most importantly, we need to be able to reason over all indicators, because it's really hard to change and identify a particular manipulation in an image or video or in text. But if you put a lot of different techniques together, the chances of fooling all of them are much lower. But at the same time, you also increase your probability of different types of false alarms. So here's an example of some of the work that was done, and I've tried to identify here what organization did it. USC ISI team which is one of the groups that I funded while I was at DARPA, used an autoencoder to be able to detect where the manipulation was based on primarily features that were steganographic in nature, in the compression features. So what happens is you get different types of features based on the compression. These two pieces of the image were compressed differently, but they were also taken likely with different cameras that have different properties in different lighting. And this type of autoencoder can do that type of stuff. Some of the people at the university, the group at the University of Maryland, colleagues of both Jimmy and I, use lighting, for example. Here's an example where you can detect the illumination distance and the illumination direction. And in pieces, this is pretty obvious that this was manipulated, but you get the idea. And so you can use that for different types of imagery. Here's an example of a plane. They were concerned about what this black thing is here on the front. They wanted to know if it was manipulated. Well, it turns out that there were even other things within this image that showed that there were inconsistencies in the lighting. There were inconsistencies in this piece of the image. Now, it turned out that this was primarily the text here that was in this, but maybe even things like this tail fin flag were different. So a lot of work was done. There were a lot of good types of algorithms. And if all you were worried about is images and whether an image has been manipulated or not, with enough training data and somebody that's not trying to cover things up, you can do a pretty good job. A face here, an airplane here, even changes to maps. But again, there's still a lot of false alarms. Some of the more interesting work that came out of this was a LSTM-based system by SRI. I'm hoping you can hear the audio here.
The standard layout for numbers is
Can you hear that? Okay. It wasn't too loud, but basically what they did is they trained a system to look at the image of the person and the phonemes that come out of the speech and what the mouth looks like when they do that. And here's an example. This one sort of
something the sound at 8,000. So just something very, very. I could even go to lower, but this is just to get.
So this is an example of that SRI system. And that second video was done just to really show that there's an audio difference. But we even had the same person try to reproduce exactly what they said and lip sync it, and they were not able to. So that even those types of things can be detected. So the basic accomplishments of this work really showed that we can take and we can do image matching at scale. We can detect manipulations in images. This was even a third or fourth generation from the New York Times, I believe. Not all techniques could do this type of manipulation detection, but there were examples of techniques that could deal with all of this type of things. So I'll talk a little bit more about what we do in terms of integrating and reasoning across different types of manipulation going forward. But that was really the goal of the media forensics program.
Dave, just a quick question. So in the wall clock photo, you're saying just you show the image and it'll give you the heat map that something there looks fishy.
Yep. In this case, it was a cut and paste technique that showed and was able to detect these pixels as being manipulated. Yep.
I see. So to what extent is that just the person who did the Photoshop just wasn't very good, or was it obvious? Like if you zoomed in and had a high res version of that, could a person tell?
Probably not. It's getting to the point where even there are techniques within Photoshop to generate this. We don't know how it was generated, but if you did get there, maybe an expert that's really good at looking for those kinds of things could have. But visually, we're getting to the point where these manipulations aren't detectable to the average eye.
I see. And in the United Nations photo, this essentially requires cross image dedupe at huge scales, right? Because you need the reference image to know what was repurposed.
No, absolutely not. This was done completely from this image alone. Yes.
Oh.
So yes, if you had the original image, but a lot of times you don't have an original image. Imagine if the Americans didn't. Well, they didn't. They didn't have the exact same angle. They didn't have the exact same image. The example that I showed was a different image, taken by a photographer, probably for the U.S. versus one for the.
I see. So these are detections in isolation without
Yes.
doing large scale near dupe detection or something.
Except for, in this case it is, because this
Oh.
is an original photo.
Wow.
This original
Okay.
photo was here. There's no manipulation to it. So there are those tasks, but in this case, no, there was no cross image work.
Wow, that seems very impressive.
Yeah, and the results are good. But midway through the program, we had this thing show up called generative adversarial networks. And I'm sure all of you have heard of them in some way. And if not, you'll be familiar with them after this talk. But let me just give you a one slide idea of what this approach is. It's basically a system which in game theory tries to maximize both sides of a two-person game. And in this case, we have a network, a neural network, that can be trained on a lot of images to generate images, or to recognize whether an image is a face or not. Okay, so this whole system is trained. You have this differentiable function here, and you have this discriminator network that allows you to say, yes, this is a face, no, this is not a face. On the other side, you have a generator network. And imagine starting with a random image, meaning just a random set of latent variables. And what can happen here is that this differentiable function, again, a machine learning approach, generates a sample. It generates an image. And now this trained discriminator network can say, okay, is this a real face or not? And of course, at the beginning, it's going to say no, because it's a random set of pixels. And what happens then is this system, when it's known to be fake, it feeds back a small set of parameters back to this function here, and it generates a new sample. Now, if you could imagine how long this would take if I was, trying to teach you how to do handwriting, for example. But now you have these computers that have GPUs and can train these things over hours, over days. And in 2014, there was in this generative adversarial network, a face that was generated from random information. And that's the example that's right here. And what was amazing about this is that you had the situation where, this didn't exist before, but you've taught a network to generate a false face or a fake face. And if you extend this, and this exploded very, very quickly, you can imagine now having a differential discriminator network that knows what a zebra is. Yes, no, is this a zebra or this isn't? Okay, and now instead of starting with an original image of noise here, we start with an image that looks like this picture of the horse in the lower right corner. Now, if you're going here and you're looking at whether this is a zebra or not, well, of course, when you feed this sample in here, it's not going to be a zebra. But what type of loss information gets transferred back to this function? Well, do you need to have loss on the grass? Well, probably not, because most of the zebra things have grass in them, or the sky. That's part of these zebra pictures, or the trees, probably not too much there. Well, how about tails? Well, I don't know. These zebras tend to have tails. They tend to have 4 legs. They tend to have a mane. They tend to have a snout that is kind of long. What's the only difference? It's basically the stripes, right? So that information, because it's further from the original image when you compare these two, gets fed back into the network. And what you wind up with is an original image and then a GAN generated image that transforms this horse to a zebra. It's essentially a teacher-student network. And there have been a lot of very interesting work here where you can give an input of a street scene here, and it will actually generate the output of that really looks like a street scene. So you give it a lot of street scenes, then you give it a segmentation, and it generates this output, making a Google map look like, or making a scene, overhead scene look like a Google map, even sketches. So there's lots of different things that have come out of this. And what's scary is you can go to the internet, you can look for things, and if you search for do not exist, or images that do not exist, you'll find lots of things that were GAN generated. These cats do not exist. And it's hard to believe these cats weren't in the training set. There weren't necessarily cats that looked exactly like this in the training set. These don't exist. The people that don't exist, you can't find in those training sets these people anywhere. And people are using this for to generate rental information, to generate resumes, even songs, just about anything you can think of that AI, a human intelligent person, would need to do to either create this in Photoshop, be an artist to create it, or find it on the internet. All of these types of things can be generated. So how is this going to be used for misinformation? Well, there was a concern, and I'll show you a couple examples. By 2019, only 5, or 2017 in this case, only 4 years after the original generative adversarial networks came out, you could generate photorealistic images of people. This was trained on the Celebrity DB data set, so it looks like a celebrity. There was also audio that was generated.
This night, I am happy to share with you a small announcement about a cool startup called Live. They launched today their web.
And so Obama didn't advertise for this company. This system was trained, and I'll talk a little bit more about this, from his Oval Office speeches, and it can now replicate his voice, and it can represent him and his movements in a reasonable way. There's also threats of refinement. Here's an eye. This was actually a system that was used to generate and test gaze in phones, Apple in particular. What they needed to do was basically understand exactly where somebody was looking. And of course, you don't have an eye tracker on an iPhone. The iPhone is moving, so traditional eye tracking wouldn't work. And what they did is they took some synthetic data and they tried to train their system on that, and it failed miserably. Well, now what they're doing is they're taking these images, they're preserving and using a refiner to make realistic eyes. You can use it for face aging, you can use it for manipulation, and even showing that you can change classifiers and launder images in very meaningful ways. So these are the kinds of threats that DARPA is interested in looking at, and that was the real focus of that program. And we're even using these generative adversarial networks in a number of different ways now. We're part of the CITER program, the Center for Information Technology Research. We use these types of manipulations to generate morphed images. The security concern here, of course, is you have a bad guy, you have a good guy, they kind of look like each other. You can generate a morph that would pass human muster on both sides and maybe even automated means. What happens then is the good guy generates a passport with his picture on it, but the bad guy can use that passport because he passes all of those hurdles. So we're using it for generation, detection, and evaluation of these types of things. But let's talk a little bit more now about what types of things are happening in the world. What about text? Well, you've probably heard of OpenAI. This was the organization that was founded by Elon Musk, among others, and it explores sort of all aspects of AI. But what they've really become famous for, and this is probably one of Jimmy's areas, is these generative pre-trained transformer models, or GPT. So there were 3 papers. We're up to GPT-3 now. And what's incredibly important about these is they are able to do unsupervised generation of text. So the same way that these images were generated originally, now they can do it by text. But what's scary here is you'll notice that this is a scale in the billions of parameters. And before this, BERT was one of the language models that was trained with 340 million parameters, and it did pretty well in a lot of classification type things. It extended the fact that, you know, previous work, you could only, like LSTMs, you could only jump a few words or a couple of sentences at the end. But if you look at this from these early models here in 2018, in just 2 years, they went to models with 1.5 billion parameters. And you can imagine how much resources that would take to be able to do that, to be able to train something like that, to a model called GPT-3, which has 175 billion parameters. I understand from various sources that it costs essentially a system developed by Microsoft with 26,000 GPUs and I think over 40,000 CPUs to generate text 10 to the 12th different tokens or more. So you can see the huge difference in training and corpus size. So we can only imagine what the types of things this is going to be used for. Well, when GPT-2 came out, there was really impressive results. It was jump orders of magnitude, just like a lot of deep neural networks things did. But they chose not to release these models, citing the safety for humanity. And anybody that knows Musk, he really feels that that this singularity is going to occur soon, or sooner rather than later, where basically AI systems get more have better techniques than humans do, and they can start teaching themselves, and then they can go rogue. The truth of the matter is, I don't think that that's anywhere near happening. We have such narrow things with AI. Nevertheless, this would have been a considerable problem for detecting manipulated or detecting real versus fake news. But there were some independent evaluators that were given access to this. And let me just give you an example of how incredible these models really are. So here's a unicorn example. Tell me about unicorns. And they had like a sentence. Okay, so you can only have like a sentence of input. Then this GPT-2 model generated this text. Dr. Perez believes that unicorns may have originated in Argentina, where animals were believed to be descendants of a lost race of people, and those humans arrived, before humans arrived in South America. If you read that, you would probably believe that that is something that somebody could have written. And if you, I don't know if anybody up there in Canada believes in unicorns, but if you did, or you didn't know that unicorns didn't exist, you might believe something like this because it's very well written. There aren't inconsistencies in it. But the fact is, there's nothing you can do to disprove this text, because if you look at it, you can say where unicorns originated. Well, there's nobody going to say Argentina, but it's also not going to say that this is fake. They'll say that unicorns are fake, but those types of things. So let me give you a couple more examples. The creatures were created when human and a unicorn met each other in a time before human civilization. Well, a little bit of inconsistency there. You have a human and a unicorn meeting before human civilization, but these types of things are consistent. Perez is a name that you might think of being in South America. And we know that there are other incidents where there are hidden people, things that come out of South America that we didn't know about before. And even things like here, where the text starts to talk about, well, if you really want to know, you have to look through DNA, and that maybe it's an alien race. All of these things are just incredible from just tell me about unicorns. So why is this really a concern? Well, first of all, there's no ability to fact check. There's a mix of fiction and fact. The language generation is really impressive. One example that one of the researchers that were given access to this noted that there are plurals that were generated that we wouldn't normally use in our language. But if you were a linguist, you would be generating them in a very similar way. There's a concern that this might one day replace authors. There's also high environmental costs. If you took the equivalent of months and on thousands and thousands of GPUs to generate this, what is the concern for that? And it could also be used for code writing. People have started to do that, to write code. So now imagine what would happen. Well, what if these models got out? How could they be used for nefarious purposes? Well, the GPT-3 is shared as a service. So basically what they're doing is they're acknowledging this type of manipulation and the things that it can do, but they're keeping an eye on it. So you use it as a surface. If they start to notice that you're using it for bad purposes, they can cut you off. Okay, so that's a big concern, is how we can generate this type of material. Something that you might have heard of that's a little bit more in the news is the term deepfakes. Now, Deepfakes was a Reddit user who generated images using these GAN-style manipulations, where you would take and you would overlay a face of someone on a video. Unfortunately, the first applications were often revenge type applications and often pornographic, where they took videos and they overlaid a celebrity's face. Well, you need to be able to have a lot of faces. That was the reason that celebrities were used in these types of application. But this is something that has been released. You can get an application on your desktop. One AI course that I taught, I asked students to do that, and they were able to generate in an evening this type of software. So it's really plug and play. So here's an example of a video of a woman and Nicolas Cage's face overlaid on it. And somehow Nicolas Cage sort of became the poster child for deepfakes, and is really used in a lot of examples. And it looks really realistic. Now, to Jimmy's comment before, if you get in there and you look at things, you can find little minor inconsistencies, but you can't do that at scale right now. So this has been used. Here's an example of a video. This is not a deep fake. This is a cheap fake. So let me show you this so that you kind of know the difference here.
Since we took
Here is the real video of House Speaker Nancy Pelosi.
and then he had a press conference in the Rose Garden with all this sort of visuals.
Now the doctor video in which she appears to be impaired.
And then he had a press conference in the Rose Garden with all this Sure.
So the reason this is called a cheap fake, also, and incidentally, I've had a little bit of trouble with my internet. So if I
Sort of
drop out,
visuals.
That
I will,
more
I'll
than
be back. It just drops out very, not very often, but if it does, it comes back pretty quickly. So this was done simply by slowing down the video. And it was tweeted by our president and a number of other people. And a lot of people believed it, that Nancy Pelosi was, seriously impaired, drunk, and all of these types of things can get out and make an impact on our elections and different things. Here's an example of another one. This is Mark Zuckerberg, and you can listen to what he says here. You can see the face. It looks like him. You can look at the mouth and see how it works when he's there.
I wish I could keep telling you that our mission in life is connecting people, but it isn't. We just want to predict your future behaviors. Spectre showed me how to manipulate you into sharing intimate data about yourself and all those you love for free. The more you express yourself, the more we own you.
Okay, so of course, that's nothing that he would ever say, but it was very easy to generate that based on audio that was there and different types of puppeteering techniques. So we've seen people that you can take a video of a person and you can replicate their appearance in a video. I don't have a video for these, but these are all videos. You can do facial expressions. In this case, the puppeteer is doing a facial expression, and in the other video, it's being replicated. Even head tilts, mannerisms, and voices are very common, but right now, not mannerisms. So you have to have the puppeteer that can do those types of facial expressions and things like that. We can't generate that. And really independent motions we can't generate right now. So if you took, and you can't generate a video the same way with a GAN as you did with the previous work. So of course, this was an election concern. And there were a number of different congressional displays here in the US where I was able to testify on artificial intelligence and the National Security Council in concern over these types of things, in terms of weaponizing these, in terms of detecting what were out there. But the hurdles really came with the idea that on one side, the group is interested in reducing misinformation. And the Republicans, of course, are saying, oh, you're restricting free speech. One of the biggest things that came out of this is that we have in the Communication Decency Act something called Section 230. And the lawyers in my world really view this as the biggest free speech piece of any act that's ever been published. And basically what it says, this Communication Decency Act realized that the internet needed to be sort of a Wild West, but they wanted to tame it in some way. So they basically said that that there are certain types of information that aren't allowed, things that are crimes, things that are exploiting children, different types of things like that. But misinformation wasn't. In fact, the Section 230 of the Communication Decency Act says that no provider can be held responsible for anything that they host. And this is really where the hurdle is, that we don't have any legal precedent right now for telling Facebook that they need to be able to, they have to take down misinformation. Now, you'll see that sometimes they are now, but that's a business decision. It's not a legal decision. But the truth of the matter is, in the 2020 election, none of this happened. None of these deep fakes were really a major problem. And part of it is because you do need a lot of data to train these individual components, but it's coming, that this could be weaponized in the way that happened in 2016. Now, there's an incredible pace of synthetic media generation. just from 2018, where you had single modality interactive audio, you had face guided generation, that's sort of the puppeteering, to things where you're completely generating these types of fake dating profiles. In this case, it's a Airbnb type thing that was generated completely from scratch. So you can generate beds easily, but there are problems with this, okay? And this is where the community is going, is in this consistency in these multimodal different types of manipulation. So there's a picture of a guy here and his name is Ann. You have a bathroom with seating for 2 or more people. You have 24/7 carpeted laundry, just things that are inconsistent and get generated that aren't really good. Now, if a human did this, of course, they wouldn't make those mistakes. So the question is, can we exploit those things? Can we look at this and say, okay, the detection that we have, in particular, you know, as Jimmy said, for images, yes, we can detect those types of things, but they're all very stovepiped, okay? We have techniques that work on one piece, but we don't have things that work on other things. So the idea here, and I'll draw your attention sort of to this reasoning piece here. We have to be able to detect things, but with high false alarm. And we want to be able to do it in all sorts of media, text, image, audio, video. So you're given a piece of news with a reporting, you have all of this. Can you do this? Can you then take this and do attribution? Can we say who was doing this? What tools were used to do this manipulation? And then most important, can you characterize this information? Because a lot of times the type of stuff we see is completely benign. It's not anything of interest. Maybe it was done for humor, but if it's polarizing, if it's trying to be a call to arms, if it's viral, if there's really an impact, we want to be able to characterize those systems. So this is where DARPA stepped in with the Semaphore program, Semantic Media Forensics or Semantic Forensics. And the challenges that get presented in this program, first of all, are multimedia, multimodal text, image, audio, and video, where the previous program was primarily just text. Just image and video. And we want to do all 3 of these components. And we want to target generative models. We want to search for manipulated media. We want to know if media has just been inconsistent. So for example, if you have an image that's misrepresenting what's in the text, and these are all very, very hard problems. And of course, you eventually want the media intent. This is just showing some work in deepfake detection from Professor Sue Liu. I recruited him here from Albany. And you can see that there are different techniques that have different levels of results for different types of video. Some use facial features, some use voice. But the idea is, can you bring all of these things together? So here's one task that we're addressing here at UB, and that's the semantic inconsistency. So if this caption here for this example said, school children enjoy recess, semantically that's implausible. So a human would have no problem questioning this type of a caption. And we're getting pretty good at this type of stuff. There's no children here. If you know what recess is, it's outdoors, this is indoors. And the same way on the image side. So we can embed image features and we can do the text features. And this is pretty easy. Well, in this case, semantic that says that Merkel and Putin meet. So that's semantically possible, but we don't know anything about it. So we would say, yeah, that's hard to determine whether this caption is wrong. Then it says, and Merkel and Putin agree, and they're aligned to benefit things. Well, contextually, it's possible, but it's implausible because we know where Merkel and we know where Putin stand on some of these things. So previously, a lot of this work focused on these components to address things independently. We have images that we could train on these systems. We have semantic models, either using transformers, GPT models, or earlier BERT models. but we don't really have anything to bring them together. So we want to address this problem by being able to look at the volume of content and address the reasoning in machine learning. And it requires context. It requires context not only from this information that's here, but also all the other articles that might be out there. The source. All of these things could be information that you would go to allow some type of reasoning that reasons about the context. So maybe there's other images posted on the internet, this exact same image with different captions. Maybe this comes from an organization that's known to be a purporter of misinformation. Maybe it comes from a right-wing organization that views things differently and is trying to move the scales a little bit. So what we did for this is basically learn a joint space model representation where we have the article and we have the text. We might have the caption as well. So in this case, it's more than just a caption on an image. It's an article. And so you have all three of those inputs. And the goal is to be able to bring them together. So our first attempt was to train what we call a Siamese convolutional neural network to learn the distinguishable features. So for example, indoor, outdoor, things that you would say in the text. Now, not all the features are going to be overlapping and consistent, but we were able to take these models, train them on the video and on the text, and be able to generate results in the high 80% for inconsistencies in news, and even in Twitter data sets, we could generate these inconsistencies. Now, whether this can be done at scale, again, these were data sets that had probably 20 to 30% inconsistencies. As you get more of the needle in the haystack, you have bigger problems. So another area, another task within this program that we addressed was tampered media. So an image and an image level manipulation label are what are the inputs. And the output is a localization map to localize the manipulation of at the pixel level. Now, in this case, this is not a system that was supervised. It is just the image and the tag that says it was manipulated. This, of course, is not necessarily the best approach right now, but if we want to extend these types of techniques to other types of media, then these are the kinds of components that we need to address. So previously, these methods operated under the assumption that you were given a set of images that were tampered with, and they were fully supervised, meaning you need a pixel level mask. And that's something that we used a lot in Metaphor previously. But it's very expensive and it's very time consuming to understand that kind of data. Now, the background was that, to our knowledge, these were not the types of things that have typically been looked at. So our approach was basically to learn patches of the image and know whether they have consistency with within the image itself. So we would look at components of the image. A lot of times they were things like people manipulated in these images. There were pretty common data sets. And unlike a autoencoder approach, this was done to optimize the patch level analysis of these images. So we adapted a fully convolutional network. We tried to improve the performance on these inconsistencies. And there are inconsistencies, again, that could come from anything. It could come from the compression of the original image. It could come from artifacts of the tool that was left, that left there. That could come from lighting. All of these things get learned in an unsupervised way. So by looking at multiple sources, multiple streams of information, the image itself, the stream from different manipulations of the actual image itself, sort of the image footprint, even images of components of the image that are not visible to humans. Again, compression parameters, things like that. By bringing all of these together, that was the approach. So here's just a few examples. This was an ablation study. So here's the example of this giant rabbit that's placed into the image. A couple people placed in here. Someone else coming in and doing a flip. All of these things, this is the ground truth at this level. And here's examples of various features that were used in the image to be able to automatically detect these types of things. And they do a pretty good job, at least detecting the regions of things that were most likely manipulated. And when we were able to compare this to other evaluations, we outperformed all of the other unsupervised methods, but even approached some of the levels of processing for supervised methods, which is pretty incredible that we can get this close with completely unsupervised method, with only having image manipulation. And of course, this type of unsupervised learning has been shown to be very effective in face detection, a lot of other image processing tasks, but something that traditionally doesn't have a very good result in particular, when you talk about the unsupervised pieces here, there was really no work that was producing any reasonable results before this. So here's just an example of some evaluation of different networks. Even the supervised networks don't do very well sometimes. These ones here basically don't get anything. But some do better at detection, but we also at least detect the areas of what's being manipulated. So there are a lot of data sets out there and a lot of public evaluation out there. And there's a lot of work and interest in being able to detect these things. But again, the concern here is not necessarily just whether something has been manipulated or not, because in some sense, almost everything gets manipulated these days. What's more of a concern is what it means. And that's really what a number of programs out there, research programs, are really focusing on. So this is an example of the Face Forensics++. It was a Google data set. And basically you wanted to know whether these faces were deep fakes or not, whether that's the real fake, the real person in these images. And the results were fairly good. They had a number of different evaluations from Google here, trying to tell whether these things have been manipulated, and some systems got as high as I think a little over 90% accuracy on these types of things. Definitely a lot of work going out. But the truth is that we still have this problem of manual content creation. And I'm not going to address that today because I wanted to just give you the idea of where we're going and what sort of concerns there are. But here's an example of an email that I got last spring. And it says, it has two sentences in it. There were some things after that. A student's vaccine status is medical information that is covered by HIPAA and is entitled to all the appropriate protections. Okay? And I don't think anybody would argue with that. If you know what HIPAA is, HIPAA basically prohibits healthcare providers and healthcare businesses, these so-called covered entities, from disclosing private information to anyone other than the patient and someone that has asked for the information and the patient has agreed to it. Okay, so that first sentence makes sense. Okay, HIPAA, we should protect it, or HIPAA, the status needs to be protected. But the second sentence says faculty should not ask students about their vaccine status. Well, if you look at this, that's also true. But it's true because that was a decision that was made by the university, by the SUNY system, that students shouldn't ask about we shouldn't ask students about their vaccine status. This was at a time before we required vaccines, right? But just having these two sentences close to each other suggests that because vaccine status is HIPAA related, that faculty shouldn't ask students about it. Well, that's completely wrong. We can ask, they don't have to tell us, because we're not covered entities. And we're not sharing the information, the person themselves, the student themselves. So these small things are things that you might not be able to say are false in how they are, but the context is really, really important. And so that's the way that the community is going to try to detect these types of things. And the problem is the scale is growing at such an incredible rate. It's really difficult to do anything more than be able to pick off the individual pieces like I've shown you and some of our work is today. So let me just summarize, and then we can answer any questions or we can have some discussion here. Large-scale automated misinformation is really not ready for prime time. And we saw that in the 2020 election. If you have something that comes out, the internet very quickly jumps on it and can disprove it with some of these tools. But the problem is the damage is done sometimes before you get it out. And the truth of the matter is that we have a lot of this type of stuff. The large-scale automated processes would require us to try to, and the real focus was, is this going to affect local elections? Is this going to affect state elections? We just don't have the processing power to be able to do this at the scale that would be something that would interfere with an election. So we don't expect the impact on campaigns that occurred in 2016, at least with this multimedia. As I said, the semantic inconsistencies are really still prevalent, and we need to focus on and be vigilant about detection in addition to attribution and characterization, because depending on what it is, we don't necessarily care about it. It might not be a national security interest, and of course the government is interested in what's a national security problem. We as the public are interested in things that are not just somebody's opinion, but spreading of misinformation. And as I said, we're seeing Twitter and we're seeing Facebook start to at least identify some of this as being inconsistent with what we would expect. But I guarantee you 100%, it's not because of the pressure from the government, it's a business decision. It's people being upset with their model and them doing this type of thing in nefarious ways. So why don't I stop there? I can stop sharing my screen, and happy to take any questions.
All right, great. Thanks so much for the talk, Dave. Since we're past the end of our allotted time, for people that want to drop off, they can do so without the social awkwardness thereof. But for others, I'm happy to stay and moderate questions. I have a few of my own, but I'll let people from the audience go first, please. If you're interested in asking a question, please turn on your video and go ahead. Okay, so while we're waiting for the audience to work up their courage, I'll ask one question. Dave, to what extent are these, channeling my DARPA speak here, known unknowns, right? In the sense that if we know that manipulation causes lighting inconsistency, causes, physics effects and et cetera, then sure, I can believe that it could be a solvable problem to detect them, right? But what about the ones in the unknown unknowns, basically, right? That we don't even know how they're going to be manipulated. So was GAN in particular, for example, a strategic surprise from your perspective?
Well, GAN definitely was. I mean, we weren't expecting, and I don't think the community was expecting these types of things, and very similar to the way that we had deep learning, where all of a sudden, we've been trying for, the early problem was digit recognition, handwritten digit recognition. We were trying to get, a few percentage points, and all of a sudden you jumped up 20% point. Now you're generating these very realistic things And how you use it though is still a challenge. And yes, it's a game. It's a race. You know, if you have what we could call trace evidence left in the images, whether they're visual, like lighting inconsistencies, or just JPEG compression things, if somebody really wants to cover those things up and they know how they were, you know, how we're detecting them, of course, they can cover these things up. There's an idea of camera fingerprinting. If you imagine, you know, 16 million pixels, and you have physical sensors in those cameras, then they all have a physical difference. Very, very, very small, but those things can be detected. And so you could imagine being able to take an image and show that it's been, or spoof that it's been taken by a different camera, a different kind of camera maybe, or a different person's camera eventually. So the same way as we have these types of fingerprints on humans, these devices have fingerprints. And so, yes, those are a lot of the unknowns. Unfortunately, the best performing techniques right now for a lot of these things are deep learning. And so it's a matter of taking and throwing a lot of data at these systems and having them detect. So we don't even know necessarily what's actually being detected. In Metaphor, you know, we did focus on some deep learning, but there were also a lot of these very specific inconsistencies.
Do you think there's something that we can learn from the security community in terms of things like you know, zero-day exploits and responsible disclosure and things like that, a process in which these, you know, flaws can be identified and disclosed in a responsible way? Is that a model we can potentially use?
Well, I think the problem is that if you have these exploits in the security community, it's like having one image that comes out, right? That's manipulated or is being used for nefarious purposes. There was an image, you know, in the 2016 election, you know, not too many people even saw it, but showed Trump, I think it was Trump, on a stage, you know, keeled over, that he had a heart attack, and, you know, these things went out into the news. And of course, you know, you could flag those types of things. You could have Facebook flag them. But the problem is here, it's almost like, you know, this isn't a piece of code that's in any way the same for multiple images. So yes, people jump on those situations. They'll jump on that, you know, those specific examples. But imagine now this is being done in scale, and you have hundreds of thousands of these potentially all at the same time. And what we're seeing, like with that example in the text, is they're not trying to just overwhelm with one single example. They're trying to move the needle just very, very small amounts. So you don't have necessarily these high profile manipulations. They're smaller ones. Make somebody look older than they really are for an election, things like that. You know, make them look intoxicated. A lot of these things, if you start having these locally and not at a national level, like our president, they're going to be much harder to detect.
All right. Any other questions from the audience? Michael, do you want to unmute, turn on your camera, and ask your question, please?
Sure. I'm just getting the camera here. Are you concerned that perhaps you know, an excessive focus in the public eye on deepfakes might sort of distract from other potential means of creating this misinformation, and you know, maybe make people more vulnerable to being fooled by something, you know, basically cause people to think it's not a deep fake means it's real?
Absolutely. I think you're right on there. The idea of deep fakes, unfortunately, has gotten, I mean, it's a cool term and it's gotten a lot of attention, but it's a very, very specific type of technique where you're manipulating and putting somebody's face on somebody else's video. But all of these other manipulations with text and things like that, you're absolutely right. There's something that comes out of this whole process that actually one of the other, a lawyer on our panel was talking about, and it's called liar's dividend. And the idea here is, you know, if you have a politician that says, oh, that's fake, that's fake, that's fake, even if it's not about them, then when you get something real about them, right, then the public is saying, well, you know, everything else is fake, this is probably fake. And it goes the other way too. So you're absolutely right that this is a much bigger problem. And what we have to do is basically train our public to understand that this type of thing is occurring, and that there's a really challenge to deal with. But nevertheless, you can talk out as much as you want and tell somebody you can prove something is fake, but if it meets their agenda, they're going to share it. And they're going to say, you know, it's real. We have in the US here, you know, we have this January 6th thing. I mean, oh, you know, people are saying that, you know, there were tourists walking into the Capitol, but then you saw that 2-hour thing where, you know, they were spraying pepper spray at the guards and trying to push through. I mean, in my opinion, a normal person couldn't even possibly think that this was, you know, not a violent thing. And you get down there, you see people talking about, you know, oh, I don't think there were any Republicans there. Those were all Democrats dressed up like, you know, like Trump supporters. So yeah, it's a real tough problem.
Thank you.
I guess we're going to end on a somewhat depressing note, but this is the world that we live in, and I guess we do all our best to try to make the world a better place in this context. Okay,
Yeah,
so let's thank Dave once again with a virtual clap for those who have stuck around, and thank you once again, Dave, for giving this talk.
Yeah. I'd love to continue to talk to you. I think we had ideas of collaboration a long time ago, and we haven't followed up on those. But I'd love to get up there eventually and keep in touch.
Okay, thanks. All right, take care, everybody.
Thank you.